Hi, in this video we discuss about depth first search for undirected graphs, and we'll use an adjacency list representation using dynamic capacity arrays. Let's consider the graph from left-hand side, and let's discuss which will be the adjacency matrix representation. Let's first look at which is a representation as a graph. So we have a set of vertices, and here the vertices are numbered. So the set will be from 0 to 12. We have 13 vertices, and we'll have the edges marked as pairs, for instance, because they are undirected. You can write them either way. 0, 1 or 1, 0 will be the same edge, but conventionally we'll put smaller vertex index first. So here we'll have 0, 1. Now, this is a representation as a mathematical graph. To create adjacency list representation, we'll use the representation data structure that was discussed in the previous videos. So we'll keep the number of vertices, and we know that there are 13 vertices from 0 to 12. So just keeping the number, we keep the entire set of vertices because they are numbered in conventionally. Then we'll keep the degrees for each vertex, which will tell me how many edges are starting from this vertex. And for each vertex, we also keep the adjacency list or links um, that are directly, so the neighbors that are linked by a direct edge with that vertex. Now for the graph in the left hand side, we'll obtain the degrees, for instance, for the vertex 0. The degree is 2 because it's connected with 1 and with 3, so the degree will be 2. And for vertex 1, the degree will be 4 because it's connected with 0, 3, 4, 2. So it has 4 neighbors. That's why the degree is 4. So that's why we have here 4. So this is degree representation, and as you see, we have an array of integers for each of the vertices from 0 to 12. Sure, for 12 is 0 because there are no edges. So you see for 12 we have 0 at the end because 12 has no edges around it. So now for each vertex, we'll also keep the adjacency list. So for 0, you can see that for 0 we have 1 and 3, which are the two adjacency elements with 0. For vertex 1, for vertex 1, it's missing here. It will appear later. Let's move to vertex 2. For vertex 2, I have only one link, which is 1. Now, this -1 is just because we have dynamic capacity arrays. I just mark -1 an element that is not occupied. Now, being dynamic capacity, here the increment is 2, so the capacity starts with 2 and it's incrementing by doubling. So that's why we have 2, 4 as the length. And if something is not there, I just put conventionally -1, can be any number. We ignore it because degree will tell me how many numbers I expect. So here I expect only one number, and that number is 1. As you can see, for 2, the link is 1. So then we move to 3, and 3 has 4. Let's bring an orange. So 3, as you can see, has 4 elements, which will be 0, 1, 4, 5. And if you look in the graph, you have 0, 1, 4, 5 are the 4 elements for free. Now, this may continue, and this way you will get all the links for a given for each and every of the vertices, and these are the adjacency arrays. Now, for 12, because there is none of none link, we keep an empty array by convention. So this is just to remind you the representation and how these are stored. Now, today we'll do something else. Today we'll look to compute the connected components for a given vertex. And the connecting component is defined as a maximal subgraph that contains all the nodes connected through a path to the given vertex. So I will try starting from a vertex to see how many other nodes I can reach, and I will take all these subgraph as my connected component. And sure, a subgraph contains a subset of vertices from the initial graph and some edges between them. Now, a maximal subgraph will contain the maximum number of nodes and edges based on the property that we define. Now, let's see for our graph which will be the connected components. And as you can see, we have three connected components here, the blue, the orange, and the green. The blue connected component, I can obtain it starting with any vertex, any blue vertex. So 0, 1, 2, 3, 4, 5, 8, and 11, all of them will lead to this blue connected component. So next I will have the orange, and again I can start with any of these orange nodes and I will obtain the same orange connected component. So 6, 7, 9, and 10 will all lead to the same connected component. And sure, the last one is single node 12. This will be also a connected component containing a single vertex, no edges, and it's typical for an isolated vertex. Now, the problem is how we design an algorithm to compute these connected components. And let's say I want to compute the connected component for vertex 8. And to do so, we'll use a color, for instance, orange, to mark the vertices in the connected component. So initially all are blue, but as I build connected components, I want to mark all the elements that I discover as belonging to the component, to the connected component. Sure, in programming, I can have a array of flags that will easily do this trick. Now, given a given vertex, for instance 8, we'll color that vertex orange, then we'll take all the adjacent vertices, and for each adjacent vertex that was not yet colored, so it's first time when I go there, I reapply the process. So again, I will color the vertex, take all the adjacent. If they are not colored, I reapply the process, and so on. So this sounds like a recursive method, and that's how it will be implemented. And at the end, after we covered all possible paths, starting from the initial vertex, I will get my component colored in orange. And all the other will remain not colored, to remain, let's say, blue in this example. Now, let's do this for the vertex set. So what we discuss will be that we'll color the vertex orange. We'll take all the vertices adjacent with the vertex 8, in this case 5 and 11. And for each adjacent vertex, if not colored, we reapply the same procedure. And sure, we'll start with 5 and is not colored, so we reapply the process. After we finish the process for 5, we'll come back for 11 and do the same. Now, at the end, after I did all of this, all the connected components will be colored orange. Now, let's see how this works. And to simplify, I will just write shorter the process. So color vertex 8 orange, take all adjacent vertices which are 5 and 11. For 5 is not colored, so I reapply the process. So let's see now how this will look for 5. And sure, I start by coloring the vertex 5 orange. I take all the adjacent vertices for 5, which are 3, 8, and 11. And for 3, which is not colored, I will reapply the process. After I finish 3, I will also need to take 8 and 11. But for now, let's concentrate on 3. So, so next one will be this one, and I will need to color it in orange. So now for 3, what we do, we color the vertex 3 in orange. We take all the adjacent vertices of 3, which will be 0, 1, 4, and 5. You see 4. And let's start with 0. And again, this 0 is not colored, so we'll be able to reapply the process for 0. So now we colored the vertex 0 orange, and we take the adjacent vertices, which is 1 and 3, and let's go first with 1, which is not colored, so we reapply the process. Now for 1, which is not colored, we color it now in orange, and then we take all adjacent vertices, which will be 0, 2, 3, and 4. All these are adjacent. And for 0, 0 it's already colored, so I do nothing. I just skip it. 2, it's not yet colored, so I will go to 2 and reapply the process. So now I color 2 in orange. So I'm here, I will color 2 in orange, and I take all adjacent vertices, which is only 1, but 1 it's already colored, so I do nothing. So I need now to come back to 1, so I'll go back to 1 and go back to the next. So for 1 I took 0, I took 2, I still need to take 3 and 4. 3 it's already colored, so I do nothing, but 4 is not colored, so I will reapply the process for 4. Now, how I reapply the process? Sure, I will first color it in orange, then I take the adjacent vertices, which in this case are 1 and 3, and for 1 I do nothing because it's already colored. For 3 I do nothing because it's already colored. So I finalize 4, and this will finalize also all the adjacent vertices with 1 from where I came here. So now I finish all the adjacent vertices with 1, so I will go back to 0. So for 0, I took 1, so I took 1, but also I need to take 3. So let's go and see what we'll do for 3. And basically, for 3, I will do nothing because it's already colored. So I will backtrack to 3. And now for 3, I took 0 first, but I also need to take 1, 4, and 5. So 1 is colored, do nothing. 4 is colored, do nothing. 5 is colored, do nothing. So basically, I finalize also 3. So finalizing 3, I will need to come back to 5 from where I came to 3. From 5, I went to 3. And 5 had 3 neighbors, 3, 8, and 11. We treated 3. Now we need to look at 8. But 8, so again, I am at 5. I treated already 3. Now I want to look at 8, which is colored, so I do nothing. So next I look at 11. And 11, it's not colored, so I will need to reapply the process for 11. And because it's not color, I will color 11 orange. Then I will take the adjacent vertices of 11, which are 5 and 8. And both 5 it's already colored, I do nothing. 8 it's already colored, I do nothing. So basically I finalize 11. So I'll need to go back now to 5 from where I came to 11 and continue 5. But for 5, I took uh, all the neighbors, 3, 8, and 11. So again, I will need to go back from 5 to 8, and 8 had two neighbors, 5 and 11. I treated 5, but I haven't treated 11. So the last step will be now to look at 11, and 11 is already colored, so I do nothing. So as you can see, I went full cycle and finished everything, and at the end, I obtained my component in orange, and all the other graph that is not connected with vertex 8 remained blue. So this way I identified by coloring the connected component for vertex 8. Now, same result will be if I start with any other vertex from this connected component, 0, 1, 2, 3, 4, 5, 11, all of them will bring the same result, but the process will be different because I will go in another direction. Now, why this is named depth first is because if we look, what I did, I will start with 8, go to 5. Then from 5, I will go to 3. From 3, I will go to 0. From 0, I will go to 1. From 1, I will try to go to 0, but I don't because 0 is already colored. But then I will go to 2. And for 2, again, I don't go back because it's already colored. Now, as you can see, I go a lot in depth. So I went as far as possible first. Then, after I finish 2, I will try to go to 3 and I will stop because it's already orange. It was already orange because I passed through it. Now, next step here, they are already colored, but I just repeat the process that we discussed, will be to go to 4. So again, if you look, it's again a long path from 8 to 4. It's in depth. Even if I turn back, basically I went in depth a lot. Sure, from 4 I will stop in all directions because they are already colored, so I will not go back. So now I will be backtrack and go back to 1, go back to 0, and sure, from 0 I cannot go here, so I'll backtrack to 3. From 3 I cannot go in other directions because they are already blocked. So I will need to backtrack to 5, and only now from 5 I will go to 11. So that's why the method is named depth first, because it's always trying to go as far as possible and then it's coming back to try another route. So go in depth first and then tries to go to siblings.